Alright, hello class. In this video we are going to be finishing our discussion on L'Hopital's rule. You can think of this as our part 2. And what we'll be looking at is at the final forms of our indeterminate forms and how we approach them. And then be looking at some of the more complicated examples that we could be dealing with. Alright, so the final indeterminate forms we're really going to look at are the ones involving powers, and specifically those are your 1 to the infinity, your 0 to the 0, and your infinity to the 0. Okay, now 0 to the 0 and infinity to the 0, the reason those are indeterminate forms is because if you think about if you have b divided by b, right? That's like b to the 1 over b to the 1. If these are positive numbers here, that's b to the 1 minus 1, so that's b to the 0. So b to the 0 is 1 if b is, say, non-zero. Because of this, it's basically a fraction. So in this case, the 0 to the 0 ends up being a 0 over 0 case based on this idea here, right? You could think of it as 0 to the 1 over 0 to the 1, which would be 0 to the 1 minus 1, which is 0 to the 0. So this is technically a 0 over 0 case, and just like that here, infinity to the 0 is also an infinity over infinity case. But you could also think of the fact that why it works this way is because 0 to any number power is 0, and any value like b that's non-zero to the 0 is 1. So 0 to the 0, well, it depends on which thing's going there fastest, right? If the base is going to 0 faster, you're going to end up with a 0. If the power is going to 0 faster, you'll probably end up with a 1. And who knows in the spectrum in between, and we have this similar idea here for infinity to the 0. A similar idea here for 1 to the infinity. It's because 1 to any power is going to be 1. However, anything greater than 1, so anything a little greater than 1 to the infinity, right, is going to go to infinity. If we're talking about the limit as, say, x goes to infinity, right? But anything a little greater than 1 to the infinity is going to be infinity, while anything a little less than 1 to the infinity is going to be 0. So, what's happening faster, right? Is the base going to 1 faster than the exponent is going to infinity? Then we'll get a 1. Is the exponent going to infinity faster than the base goes to 1? Well, then we'll either have maybe an infinity or a 0 depending on how the base is behaving. So that's why these are all indeterminate forms. Okay, now how do we deal with these indeterminate forms? And this is the most complicated of our methods, but it's going to remind you of the tower functions. How do we deal with them? Okay, we deal with these cases using logs, specifically ln, usually, because that's our nicer sort of derivative. Okay, and I think the best way to sort of describe how this works is with an example, but it's going to seem really, familiar to our tower function discussion we had before. All right, so let's say we want to find the limit as x goes to 0 from the right of x to the x. So this is a 0 to the 0 case. Okay, now here's how we deal with it. I'm going to just, there's a lot of ways we could do this, but I'm going to say let y equal x to the x. Right, this sort of is familiar to our tower function idea. We always start with that y equals x to the x. Then we're going to take the natural log of both sides. Okay, so we'll have that the natural log of y is is equal to the natural log of x to the x. And the nice thing about natural logs is that we can move that x out front. So that natural log of y is equal to x natural log of x. Okay, now, once we do that, take the natural log of both sides and simplify, then we can take the limit of the natural log of y instead of y. Okay, so we're going to look at the limit, okay, as x goes to 0 from the right of the natural log of y. So that will be the limit as x goes to 0 from the right of x, ln x. Now this is now a 0 times infinity case, right? X is going to 0. Natural log of 0 is going to negative infinity. So this is a 0 times infinity case. So we can use L'Hopital's rule. We just need to rewrite this as a fraction. And I think the best way to do that is to take our limit and move the x down into the denominator. So we have the natural log of x over 1 over x. Okay, or you could write that as x to the negative 1. Right? So now, as x goes to 0 from the right, ln of x goes to negative infinity, and 1 over x goes to positive infinity. So this is an infinity over infinity case. So now we can apply L'Hopital's rule. All right, so from here, we take the derivative of the top, which will be 1 over x, and the derivative of the bottom, which will be negative 1 over x squared. Now when we invert and multiply, we get negative 1 over x times x squared over 1. So this x will cancel with the x squared, and we're going to be left with negative x. Alright, and so since we're taking the limit as x goes to 0, this negative x goes to 0. Alright, so here's what we do now. What we found is that the limit as x goes to 0 from the right of the natural log of y is 0. In other words, natural log of y is going to 0. So if we apply our e's to get back to just y, this tells us that y is going to e to the 0, which is 1. Okay, so then the limit as x goes to 0 from the right of just y is 1. Okay, and that's how we apply this. We use the e to get back to what we started with. So this tells us, and y, if we go all the way back up here, our y is just x to the x. So that tells us that the limit as x goes to 0 from the right of x to the x is 1. Okay, and this is the method that we use essentially to deal with these x to the x cases. All right, let's look at another example here. Let's say we have the limit as x goes to infinity, 1 plus 1 over x all to the x. So as x goes to infinity, this piece in here goes to 0, right? And the exponent is going to infinity. So the whole base is going to 1 while the exponent's going to infinity. So this is a 1 to the infinity case, and we're going to approach it in much the same way. We're going to let y be 1 plus 1 over x all to the x. Then we take the natural log of both sides, get the natural log of y is equal to the natural log of 1 plus 1 over x all to the x. And here we use that log rule again, telling us that that is x times ln of 1 plus 1 over x. Okay, and now the limit as x goes to infinity of the natural log of y we can consider as the limit as x goes to infinity of x times ln of 1 plus 1 over x. So as x goes to infinity, of course, x goes to infinity. As x goes to infinity, this 1 over x goes to 0. So this is going to the natural log of 1. So this whole piece is going to 0. So once again, this becomes a 0 times infinity case. And once again, we will deal with it by rewriting it as a fraction. So we can move this x down and have the limit as x goes to infinity of the natural log of 1 plus 1 over x all over 1 over x. Now, this is going to be a 0 over 0 case, because this part here is still going to 0, but now this is a 1 over infinity, which is a 0. Okay, so now that we have a 0 over 0 case, we have this set up to use L'Hopital's rule. All right, so using L'Hopital's rule, we'll take the derivative of the top. So this is natural log of the stuff. So it will be the derivative of the stuff. So derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared, all over the stuff left alone. And this whole thing all over the derivative of 1 over x, which is going to be negative 1 over x squared. Okay, now we are going to, since we have a fraction divided by a fraction, we are going to invert and multiply. So I will leave the top fraction alone for the time being, and then multiply by the inverted form of this, which will be negative x squared over 1. Now, when we bring this negative x squared into the numerator, it's going to cancel with this 1 over x squared. Right? So this whole thing is going to end up being, all right, so the x squareds are going to cancel, or not cancel, but come out to be 1. So we will end up with 1 over 1 plus 1 over x. Now, if we remember what we were doing here, we're taking the limit as x goes to infinity. So now this piece is going to 0. So this goes to 1 over 1 plus 0, or 1. Now, we aren't done. It's easy to think that. What we found is that the natural log of y goes to 1. So that means that if we introduce our e's, that y is going to e to the 1, or just e. Okay, so that gives us our final answer here, that the limit as x goes to infinity of 1 plus 1 over x all to the x is e. Okay, let's look at another example. Okay, let's look at another example here. Say we have the limit as theta goes to 0 from the right, sine of theta raised to the tangent of theta. Well, sine of 0 is 0, tangent of 0 is 0, tangent of 0 is 0, so this is a 0 to the 0 case. So whenever we have these power cases, we're going to introduce our natural log. So I'm going to let y equal sine of theta raised to the tangent of theta, and then take the natural log of both sides. All right, so we have, once we apply our log rules here, the natural log of y is equal to tangent theta times the natural log of sine theta. Okay, and so we're actually considering the limit as theta goes to 0 from the right of now tangent theta times the natural log of sine theta. Okay, now, of course, tangent of 0 is still going to 0, so this piece is going to 0. But the natural log of sine of 0, well that, and since we're going from the right, that's going to negative infinity. So this is a 0 times infinity case. Okay, so what we're going to do, like always in these cases, is move, I always like to move the non-natural log piece down. And I like this because in this particular case, when I move tangent into the denominator, 1 over tangent I could just write as cotangent, right? So this would be the natural log of sine theta all over cotangent theta. Okay, so now that we have this, cotangent of 0 is going to be an infinity. Okay, so we've turned the 0 piece into infinity. So we now have an infinity over infinity case, meaning we can actually apply L'Hopital's rule. Okay, so we'll take the derivative of the top. Well, derivative of the top is going to be the natural log of the stuff, so it'll be the derivative of the stuff, which will be cosine theta over the stuff, which is sine theta. So let me mark that I'm using L'Hopital's rule here. All over, now the derivative of cotangent. The derivative of cotangent is going to be negative cosecant squared of theta. Okay? Well, this right here, there are a lot of ways we could approach this, but I want to try and simplify it before I start really looking at what's happening. So I'm going to start by rewriting this negative cosecant squared as 1 over sine squared. Right? So this is cosine theta over sine theta all over negative 1 over sine squared theta. So if we move this up top, we'll get cosine theta over sine theta times sine squared theta. So the sine down here will cancel with one of them up here. Okay, so this ends up being cosine theta times sine theta. And remember, we are taking the limit as theta goes to 0. So as theta goes to 0 from the right, this goes to cosine of 0, which will be 1, times sine of 0, which is 0, so we get 0. Now, it's always tempting to say that we're done, but remember, we're looking at natural log of y. So natural log of y we found goes to 0. So when we introduce our e's, this tells us that y itself is going to e to the 0, which is 1. Okay, so that tells us that the limit as theta goes to 0 from the right of sine theta raised to the tangent of theta is 1. All right, let's look at another example here. Let's say we have the limit as x goes to 0 of e to the 2x plus 1 all over 1 over x. So as x goes to 0, we'll have e to the 0, which is 1. Let me write this down here. We'll have e to the 0, which is 1, plus x, which will just go to 0, all over 1 over 0. So this looks like we're dealing with a 1 to the infinity power. Okay, so that is what we're dealing with. Okay, so this is a 1 to the infinity case. So we're going to use our natural log stuff again, right? So if we let y equal our stuff, e to the 2x plus x all over, or not all over, but raised to the 1 over x, when we take the natural log of both sides, I'm going to go ahead and skip to the 1 over x natural log e to the 2x plus x. And hey, this is already in the form of a fraction, right? So if we're looking at the limit as x goes to 0, the natural log of y, we're essentially looking at the limit as x goes to 0 of the natural log of e to the 2x plus x all over x. All right, so as x goes to 0, what's inside the natural log is going to 1. Right, so what's in here goes to 1, which means the whole numerator goes to 0 and the whole denominator goes to 0. So this is a 0 over 0 case. So there wasn't really much work to do to get this to be a L'Hopital rule candidate. Okay, so we'll take the derivative of the top, which is again the natural log of stuff. That's pretty much what always is going to happen here. So we'll get 2 e to the 2x plus 1 all over e to the 2x plus x. Okay. All over, well, the derivative of x is just 1. So really, we're simply looking at the limit as x goes to 0, 2 e to the 2x plus 1 all over e to the 2x plus x. And this shouldn't be a problem, because when we plug in the 0, we'll get 2 times e to the 0, so 2, plus 1 all over e to the 0, which is 1 plus 0. So we get 3. All right, so there we go. There is this limit taken care of, except, remember, we just found that the natural log of y is going to 3. So this tells us, when we introduce our e's, that y is going to e cubed. Okay, so that means that our final answer, if we scroll back up here, so I don't rewrite it again, the limit as x goes to 0 of e to the 2x plus x all to the 1 over x is going to e cubed. And there we go. All right, so those are the, that's the final sort of technique that we have. And that should get you rolling on the homework without much trouble, hopefully. But I do want to look at maybe 2 more examples that are just fairly complex to show that maybe L'Hopital's rule isn't always this nice, beautiful thing that we like to think it is. All right, so let's look at the limit as x goes to 1 of x ln x plus natural log of x minus 2x plus 2 all over x squared times the natural log of x all cubed. So remember, when the cube is here, we're cubing that whole ln. Now when x goes to 1, these natural logs are going to 0. So we already have a 0 in the denominator, and then right here we have a 2 times 1 plus 2, so it's negative 2 plus 2. So this is a 0 over 0 case. So thankfully there's not much extra work to do here to get started, but this is going to be one of those where the derivatives are going to be where it gives us problems, right? So we can apply L'Hopital's rule. When we take the first derivative here, that's going to be a product rule. So it'll be the derivative of the first times the second left alone, so just the natural log of x, plus x left alone times the derivative of natural log of x. So this will be x times 1 over x. So that's just the derivative of this first piece. Then plus derivative of the natural log of x, so 1 over x. Okay. Then the derivative of negative 2x, which is just negative 2. And there's the derivative of the top. Now when we go to take the derivative of the bottom, it's another product rule. So it'll be the derivative of x squared, which is 2x, times this natural log of 3x left alone, plus this x squared left alone, and now it's the derivative of this natural log of x cubed. So natural log of x cubed, when we take that derivative, okay, we're going to get 3 times the natural log of x squared times the derivative of the natural log of x. So that's 1 over x. So it's going to be 3 ln squared x times 1 over x. Okay, so I'm going to move the 1 over x out front to say that this will be 3 over x times the natural log of x squared. All right, so if we simplify this down here, this will become 1. So the 1 minus 2 will be a minus 1. So we'll have a natural log of x, okay, plus 1 over x minus 1 all over 2x natural log of x cubed, plus this will simplify to be just 3x times the natural log of x squared. Okay, unfortunately, we once again have a 0 over 0 case, right? Because when we plug in the 1, this is 0, 1 minus 1, so we have 0 up top. Then here, these ln's are going to be 0, so we have 0 plus 0, so 0 on the bottom. So we have another 0 over 0 case. So we get the privilege of using L'Hopital's rule again. Hopefully this will be it, right? So natural log of x, its derivative is 1 over x. The derivative of 1 over x is going to be minus 1 over x squared. Derivative of negative 1 is, of course, 0. And now we have a lot of really gross product rules to deal with. Okay, so for this one, it'll be derivative of the first, which is 2, times the natural log of x cubed. Okay, then plus 2x times the derivative of the natural log of x cubed, which we did here. That's going to be 3 over x times the natural log of x squared. All right, then we have this product rule to deal with. So it will be the first guy left alone, so the derivative of the first guy, 3, with the second guy left alone, right? Then it will be plus the 3x times the derivative of the second guy. So using the same idea we had before, this will be 2 times the natural log of x times 1 over x. All right, so we have this big monstrosity here. All right, but we can simplify because these x's cancel. And we have 6 ln squared and then 3 ln squared. So we should have a plus 9 ln squared. So the denominator, or the numerator, I'm going to leave the same, but we'll have 2 ln cubed x plus 9 ln squared x. And then here, this x and this x cancel. So we have plus 6 times the natural log of x. And once again, we are going to have a 0 over 0 case, because when we plug in the 1, we'll get 1 minus 1 up top, and then 0, 0, 0. So we have a 0 over 0 case. And I said it before, but hopefully for real this time, this is the last time we have to use L'Hopital's rule. So let's see. The derivative of 1 over x is going to be negative 1 over x squared. The derivative of 1 over x squared, so that's x to the negative 2. Or negative x to the negative 2, so this is going to be 2x to the negative 3. So it should be plus 2 over x cubed. All right, and already I'm seeing something better here, because when we plug in the 1 here, we'll have 2 minus 1. So the numerator is already going to 1, so that should be good. Here, there are no more product rules to worry about. All of our x's are gone. It's just ln stuff. All right, so, and we'll just use the chain rule. So this will be 6 ln squared x times 1 over x. And here we'll have plus 18 natural log of x times 1 over x. And then here it will just be plus, there's no ln squared or anything, so we're just going to get 6 over x. All right, now we should just be able to plug in the 1. Right? If you remember, x is going to 1. So when we do that, this will go to 0, this will go to 0, but this goes to 6. So we're done finally. We'll get negative 1 plus 2 over 0 plus 0 plus 6. So we end up with 1/6 as our final answer. Okay, so L'Hopital's rule overall is nice. However, there are certainly cases where it is still a bear, right? It's still a lot of work to get to the answer of the limit, but at least we can, right? This is a case where we wouldn't have been able to do anything with our previous techniques. Okay, so with that example out of the way, that seems a good place as any to call it, and I will catch you all in the next one. Cheers.